Today we will go through acidic strength of aromatic carboxylic acids, and we'll compare the acidic strength with those of aliphatic carboxylic acids, right? So the simplest aromatic acid is benzoic acid, we know. Let's write it this way. This is your simplest aromatic carboxylic acid, benzoic acid, right? This is your carboxyl group which is attached to the benzene ring. Coming on to aliphatic acid, this is your aliphatic acid, acetic acid, right? And what we say is that aromatic carboxylic acids are stronger than aliphatic carboxylic acids, right? We'll look into the reason why. Now, if you look into the structure, from the basic structure of these two acids, we know that this is the carboxylic acid which is common in both aliphatic and aromatic acids, any acid, right? So here this carboxylic acid is connected to methyl group, right? And carbon atom of this methyl group is sp3 hybridized. If you look at benzoic acid, you have this benzene ring which is attached to the carboxylic group, right? So this carbon atom of carboxylic group is connected to this carbon atom of benzene ring which is sp2 hybridized, right? Just notice the difference. Here carbon atom of carboxylic group is connected to sp3 hybridized carbon of methyl group. Here carbon atom of carboxylic group is connected to sp2 hybridized carbon of benzene ring, right? And we know that how does the hybridization, one basic thing is how does the hybridization of carbon atom will affect the acidic strength, right? As you move from sp3, right, to sp, right, the acidic strength increases. As the hybridization of carbon atom increases from sp3 to sp, the acidic strength increases. Why? Because in comparison to sp3, your sp2 and sp has more S character, right? If we talk about sp, you have 50% S character, right? And you have more S character in sp2 compared to sp3, right? And more is the S character, more is the acidity, right? Just write it over here. More is the S character, more is the acidity. More is the acidity. And how increasing S character increases the acidity? Because as the S character increases, the electronegativity also increases, right? Because of more electronegativity. More is the S character, more is the acidity because of more electronegativity, right, of carbon atom in this case, right? Now what causes more S character to have more acidity? If you remember, we have done this in atomic structure, that first of all, electronegativity is ability to attract the shared pair of electrons, right? And we know that if you look at the structure of atom, your S orbital, right, is closest to the nucleus, right? So electrons, and we know that nucleus is positively charged, so electrons that are in S orbitals are more tightly attracted, right? So electrons in S orbital, since they are more tightly attracted to the nucleus of the atom, so they have more electronegativity, right? So more S character means more acidity, right? And more electronegativity. Now since this sp2 hybridized carbon atom, right, this has more S character, so this is more electronegative than this, right? So it has weak minus I effect, right? So benzene ring, due to sp2 hybridized carbon atom, has weak minus I effect, so it will withdraw electron from the carboxyl carbon and your oxygen of OH bond, right? So here, since it is sp3 hybridized, so electronegativity is less, and we know that this is electron releasing group, methyl group, right? And electron releasing groups, we have discussed this before in the previous lecture. Electron releasing groups will make this OH bond a stronger bond, right? And that will decrease the acidic strength, because if this bond is a stronger bond, it will make the release of hydrogen ion difficult, right? So due to sp2 hybridized carbon atom, right, we have minus I effect, right? Benzene exerts minus I effect, but this benzene ring also exerts your plus I effect, right, which is your electron donating. We know that benzene is electron rich molecule, right, because of its pi system. So benzene has plus I effect also, and due to sp2 hybridized carbon atom, which is more electronegative, since it is more electronegative, so it will attract electron towards itself. It has minus I effect, electron withdrawing effect. So due to minus I effect, it will withdraw electrons from carboxyl group, and due to plus I effect, it will release electron towards carboxyl group. So which one of these two win? Plus I effect will win. That is, overall effect would be plus I effect due to benzene ring, right? Overall effect would be plus I effect, that is electron donating. Overall effect of benzene ring is electron donating effect, right? Now, if you come, what we said in the beginning, that benzoic acid is a strong acid compared to your acetic acid or any aliphatic acid. In general, aromatic carboxylic acids are stronger than aliphatic carboxylic acids. Coming on to this, your methyl group is electron releasing, right? Here benzene is also electron donating or electron releasing. But since both this shows plus I effect, right? But electron releasing effect is more in this. In case of aliphatic carboxylic acid, the alkyl group has more electron releasing effect, that is, it has more plus I effect. So it will any alkyl group in case of aliphatic carboxylic acid will release electrons more strongly towards this carboxylic group. That will make this bond a stronger bond, right? How? Just a quick recap. When electrons would be released towards carbon and oxygen, it will make this oxygen more negative. It will intensify the negative charge, right? And you have a bond pair of electron here. Now when you have more negative charge, this bond pair of electron is also negative, so it will repel the bond pair of electron. The negative charge on this oxygen atom, the increased one, will repel this bond pair towards hydrogen atom, right? Now this bond pair has more control on this hydrogen atom. It will attract more strongly this hydrogen atom, right? Due to which this bond will become a strong bond and release of hydrogen atom will become difficult. This is the plus I effect. This is the effect of plus I, right? Or the electron releasing effect. Because we know that it is due to this bond pair of electron that these two atoms are together in this OH bond, right? So when this bond pair is more towards oxygen, it will attract this hydrogen atom. When this bond pair of electron is more towards hydrogen atom, it will attract the hydrogen atom more strongly, right? So due to which it is more tightly bonded in this OH bond, right? So its release will become difficult, right? But this plus I effect in benzoic acid, that is plus I effect of benzene ring in benzoic acid, is weaker than any of the alkyl groups in aliphatic acids, since this electron releasing effect, right, that makes the release of this hydrogen atom difficult, that will finally reduce the acidic strength, right? This effect is weaker in case of benzoic acids. That means since this effect is weaker in benzoic acid, here this bond will become strong less compared to in aliphatic carboxylic acids. So here the release of this hydrogen atom will be easier compared to its release in aliphatic carboxylic acids, because here you have a stronger plus I effect and here you have a weaker plus I effect, right? So due to weaker plus I effect of benzene ring, right, in aromatic acids, due to weaker plus I effect of benzene ring in aromatic acids, right, your aromatic carboxylic acids are strong acids, are stronger than aliphatic carboxylic acids, right? I hope this is clear, right? The plus I effect, just remember here one thing, the plus I effect of benzene ring, right, plus I effect of this benzene ring is less compared to plus I effect of any alkyl group in case of aliphatic acids, is less compared to plus I effect of any alkyl group, right, in aliphatic acids. Since plus I effect is weaker here, so this makes this OH bond less strong, so release of hydrogen is easier. When release of hydrogen is easier, we say it's a stronger acid because it can easily release hydrogen atoms, due to which a compound is declared as an acidic compound, right? I hope this is clear. Now let's look at this effect of substituents on aromatic carboxylic acids, right? In aromatic carboxylic acids, substituents are present at ortho. These two are ortho positions and this is your para position and this is your meta position, right? Substituents can be at ortho, meta or para position, right? So like we have done in previous section, in previous lecture, how does electron withdrawing group and electron donating group affects the acidic strength of aliphatic carboxylic acid, right? Electron withdrawing group, here like we have studied here in this explanation only, that electron releasing group will make this a stronger bond, right, and will make the release of hydrogen ion difficult. So electron releasing group in case of benzoic acid or aromatic carboxylic acids also will decrease the acidic strength, right, whereas electron withdrawing groups like nitro group, Cl group will increase the acidic strength, right? And the position of the group, the position of the electron withdrawing group or electron donating group will also affect, right, whether whether the group is at ortho position, para position or at meta position, right? So let's quickly see. You have let's if you have a methyl group, right, if the substituent is a methyl group, right, it can be at ortho position, it can be at meta position, it can also be at para position, right? So we know that methyl group is an electron releasing group, right? So what it will do is, since it is an electron releasing group, it will release electrons, right, towards the benzene ring or towards the carboxyl group. When it will release electron, it will make this bond the OH bond, like here a stronger bond, right? Since it is releasing electron, so it will increase the negative charge at this oxygen and at this carbon. Since electron density is increased at carbon, right, so it will make this bond a stronger bond, so release of hydrogen would become difficult, right? Similarly, you have at meta position, you have here. Now one thing we need to consider in the different isomers, that whether the group is electron withdrawing or electron donating, when it is present at para position, its effect is more, right? So here the electron releasing effect would be more compared to when it is present at meta position, right? So we say that meta isomer is stronger acid than your para isomer, right? Because when the group is present at para position, it releases electron more strongly, right? So when it releases electron more strongly, this will become more negative and the release of hydrogen ion will become difficult, right? So this makes it a weaker acid. So we say that para acid, right, or this para acid, when this methyl group is present at para position, this is a weaker acid compared to when this is present at your meta position, right? So we'll write it like this. So if you compare the acidic strength of these two with your unsubstituted acid, which is your carboxylic acid, that what would be the strength? And one important thing is, when the substituent is present at ortho position, it will make the acid a strongest acid. Why? Because of some steric and electronic factors. The complete reason is not known how the substituent at ortho position will make it a strongest acid, but we say that possibly it is due to some electronic and steric factors that it makes it a strongest acid, right? So this is a orthotoluic acid, right? This is metatoluic acid, and this is your paratoluic acid, and this is your carboxylic acid. Now let's see how it will affect the acidic strength. We say that when your substituent is present at ortho position, that would be the strongest acid. Whether it is electron releasing or electron donating, it will make it a strongest acid, right? So this would be the strongest acid, stronger than even your carboxylic benzoic acid, right? Now this benzoic acid, right, is stronger than meta acid, meta isomer, metatoluic acid. This is stronger than metatoluic acid, and metatoluic acid is stronger than paratoluic acid, like this. Right? So this is the way your acid strength decreases. In this direction, the acidic strength decreases. This is the strongest acid, then comes this, then comes this, then comes this. What is the reason? Important thing is that when your substituent is at para position, the effect is more. Its effect is more, right? And in case of ortho isomer will make an acid, or it will make the substituted acid a strongest acid, right? Why? Because of some steric and electronic factors. We'll understand this a little more. Right, when we say electronic factors, maybe some kind of electrostatic interactions, right? Like in case of hydroxybenzoic acid, we have hydrogen bonding that will stabilize the carboxylate ion, right? Various things. But this reason is not fully understood by the chemists, right? So important thing to consider is, when a substituent is present at para position, it will release electrons more strongly. That will make this bond a stronger bond, right? So this is the weakest acid. But when the substituent is present at meta position, this is your meta position, its effect is less, right? So this is a stronger acid than this. And when you have an orthoisomer, it will make the acid strongest acid, right? This is important. Now let's look at electron withdrawing substituent. Electron withdrawing substituent like nitro group. Nitro group is an electron withdrawing substituent. Right, so in case of electron withdrawing substituent, like I said, electron withdrawing substituent, this was your electron releasing substituent. Right, electron releasing substituent will decrease the acidic strength. Right, so this is your strongest acid, then your this, right, then comes this, then this is the weakest acid. Here here the acidic strength is going down, it's decreasing. Acidic strength is decreasing in this direction, right? So this is it. Now let's come to electron withdrawing substituent. Right, if we talk about electron withdrawing substituent, let's take example of nitrobenzoic acid. Right, so when nitrobenzoic, let me just, you have an orthoisomer. When nitro is present at NO2, you have orthoisomer. Right, and if it is present at, this is ortho, this is your para, right, and this is your meta. Right, substituent is present at meta. Ortho para, ortho nitrobenzoic acid, para nitrobenzoic acid, and meta nitrobenzoic acid. Right. And we know that electron withdrawing substituent will increase the acidic strength. How? When you have an electron withdrawing substituent, let's take nitro group, what it will do is it will withdraw electron towards itself. Right? When it will withdraw electron towards itself, it will make this OH bond a weaker bond. Right? Because you have less negative charge now. When you have less negative charge, it can attract this bond pair towards itself more strongly. When it will attract the bond pair towards itself, then this bond pair is away from hydrogen atom. When this bond pair is away from hydrogen atom, it has less control on this hydrogen atom. Right? So now this hydrogen atom can be easily lost. That is why electron withdrawing groups increases the acidic strength, because in that case this OH bond will become weak bond because of displacement of this bond pair towards more electronegative atom or towards oxygen atom. Right? That makes the release of hydrogen ion easier. When the release of hydrogen ion is easier, we have more hydrogen ions. That means the compound is more acidic. Right? So nitro group, which is an electron withdrawing group, these are electron withdrawing groups. Right? That will increase the acidic strength. It will increase the acid strength. Right? But here also you have same thing. When this substituent is present at para position, it has more effect. Right? That means it will withdraw electron density more strongly when nitro group is present at para position. When compared to when it is present at meta position, it has less effect. Right? So this would be a stronger acid compared to this. Right? Para nitrobenzoic acid is would be stronger acid than meta nitrobenzoic acid because of stronger electron withdrawing group at para position. Right? Whereas, like we discussed here, orthoisomer would be the strongest acid, right, due to some steric and electronic factors. So this would be strongest acid, right? Then comes your this, then your this, then you have your benzoic acid. So how this electron withdrawing group will affect the acidity of benzoic acid. When the substituent is present at ortho position, it makes orthonitrobenzoic acid the strongest acid. When it is present at para position, right, its effect is more, right? So this, but this is the ortho isomer, right? When the substituent is present at ortho position, it would be strongest acid. This is your strongest acid, irrespective of whether it is electron releasing or electron withdrawing. Now this is strongest. Then comes your this para isomer, because at para position the electron withdrawing effect is more, right? Then comes your meta. So here electron withdrawal is more strong, right? So this makes this bond a weaker bond, right? Because effect is more at para position. So this would be stronger acid than meta isomer, meta nitrobenzoic acid. Why? Because this has less electron withdrawing effect compared to para isomer, right? So benzoic acid would be weaker. This is strongest, this is weaker, right? So the acid strength decreases in this direction. Acid strength decreases in this direction, right? I hope this is clear. Now let's take one example of the hydroxybenzoic acids, right? Let's quickly look at hydroxybenzoic acid. Hydroxybenzoic acid would be an electron releasing, right? Hydroxyl group is an electron releasing group. So let's quickly look at it. So when you have, say, hydroxyl group, so hydroxyl group is an electron releasing group. When it is present at ortho, it would be strongest acid. When it is present at para, effect is more compared to when it is present at meta, right? So since hydroxyl group is an electron releasing group, it makes the acid unsubstituted benzoic acid a weaker acid, right? But irrespective of electron releasing or electron withdrawing, when the substituent is present at ortho position, it would be declared as the strongest acid, right? Right, so when OH is present at here, it would be the strongest acid, right? And when it is present at meta, the effect is less. Here the effect is less, electron releasing effect is less, right? So this would be stronger compared to para isomer, because at para isomer, para orthohydroxybenzoic acid, this OH group has more effect. When it is present at para position, it will release electron more strongly, so it will make this bond a stronger bond, right? And release of hydrogen ion will become difficult. So this would be weaker compared to meta isomer than your benzoic acid, right? I hope this is clear. Now one thing to understand here is why this is more stronger acid for orthohydroxybenzoic acid. If you look at the ionization of orthohydroxybenzoic acid, let me just quickly show you. Your orthohydroxybenzoic acid, it is stabilized due to hydrogen bonding. That is why this is strongest. Right? When we add it to water, this hydrogen ion would be released. This is negative, this is OH, so you have hydrogen bonding. You have hydrogen of this OH, between hydrogen of this OH and oxygen of this ion, right? You have highly electronegative atom, oxygen atom, you have hydrogen bonding here, right? And you have hydrogen ion. So this is stabilized, this ion is stabilized due to hydrogen bonding, right? Since this is more stable, right, compared to others. This is the